I'm Martha Marshall. I am a member of the Fab Friday General Topic Committee, and we have other members of the committee here. If you guys just would briefly stand up so that these are people you could talk to sometimes if you want to ask more questions. Just stand up briefly if you're a member of the committee. And we have Laura Patlove, and we have Susan Kaiser, and we have, all right, there's Anne-Marie Clancy, we have Jane Yokoyama, and we have, and Janie Wilson is right here. And she's got some health issues that she's still recovering from an accident, so she's okay. She doesn't have to stand up for that, right? So Dr. Doug Miller, who is wonderful, he told me this fun story that they actually have a grant that their students are using to study hurricanes. I can probably tell you some more about that, which I think is fascinating because most of those students actually live through the hurricane, and UNCA being shut down and the students having to be sent to live in dormitories all over North and South Carolina and taking classes totally on Zoom for a while. It was a fascinating experience. So these kids really care about the results of that research. It's all yours.
Thank you very much, Martha. So my name is Doug Miller. I graduated with my PhD from Purdue University, and after that went to do a postdoc for about 8 years. That's long for doing a postdoc. But you'll understand why when I tell you where it was. It was out in Monterey, California with the Naval Postgraduate School. So that was a place I had never lived in my life and learned a lot about the unique weather along the coastal zone of the West Coast. And then after finishing there, I came here in 2004, just in time to enjoy Francis and Ivan and our new fence getting knocked down by a tree. So we had a little bit of understanding of what the potential was with hurricanes encountering Western North Carolina. Today I'm going to focus primarily on talking about things that are maybe more common, that sometimes are worse because we have mountains in our backyard, and sometimes, well, quite often actually, are not nearly as bad because the mountains actually, in a way, kind of protect us from them happening. So I'm going to talk about both warm season, which of course that generally means thunderstorm scenarios, and then also talk about cool season examples. We of course are rounding the corner from summer and starting to think about heading into the cool season, and so hopefully you'll get some preparation for what we might see coming up this next winter season. So let's first start with some basic basic constructs of the different types of weather animals that we see here in Western North Carolina. So wintertime cool season, we're dealing with what we call the mid-latitude cyclone. And this was kind of identified way back in the early 1900s by the early meteorologists that were based in Bergen, Norway. And much of what they observed, unbelievably, with very little technology, still holds true as our conceptual model of what these mid-latitude wintertime cyclones look like. So these are the kinds of features that you typically see on the TV weather, right? The little L means it's a relative low pressure center there. And of course, you've got the fronts that are extending from the center of that low pressure system. Of course, the blue is the cold front and the red is the warm front. And by and large, again, what they identified way back in the early 1900s still holds true today. But technology, of course, has uncovered a lot of other structures and details that weren't possible back in the early 1900s. So one of the analyses that was done, kind of very important to improving our conceptual model, was done at Penn State University back in the 1980s. And it was the identification of these primary airstreams that flow through these storms. And I want to highlight in the orangish arrow, that's one of the airstreams that we call the warm conveyor belt. And of course that implies kind of the origin of where those air parcels, those little like balloon-like pieces of air come from. So if it's a warm conveyor belt, that generally means it's coming from warm areas, so tropics, subtropics. And of course, if they're warm, that also is going to imply that they carry with them a fair amount of water vapor, so they're quite humid air masses. And this warm conveyor belt actually is responsible for creating most of the cloud and the precipitation in our mid-latitude weather systems. So in the wintertime, the warm conveyor belt is going to be what causes precipitation to fall from the sky. But every once in a while, we get a special feature that tags along right near that warm conveyor belt that we call an atmospheric river. And this is a satellite snapshot of basically water vapor added up throughout the entire depth of the atmosphere. So the warmer colors that you see on the right-hand side of that color bar, those represent more humid conditions, and then of course the left-hand side are more dry air conditions. And if you look carefully, you see a nice little ribbon, narrow area of relatively high water vapor content, and that is how we identify atmospheric rivers. Now there's an entire research center and also operations center out associated with the University of California, San Diego, that monitors these things primarily for the West Coast. And you've probably seen in the news, whenever it gets to be wintertime, if there is a pretty powerful atmospheric river getting ready to make its way into the West Coast, that's probably going to make the national news, because when they get a strong atmospheric river out west, that generally means that they're going to get a lot of precipitation along the coastal mountains. And of course, the problem out there is right before the winter season, they usually have their primary wildfire season. And anytime you get wildfires that create a disruption to the trees and the vegetation, that basically destabilizes the soil, so that when these atmospheric rivers come in the following winter, it increases the likelihood or the chances of a mudslide or landslide. And so that's why they monitor it pretty closely. We get atmospheric rivers here as well, and I'll show you an example of one here a little bit later on. So these are our primarily wintertime weather makers. Sometimes snow, not as much recently, but definitely very much bringing in heavy rainfall. So now let's analyze more the warm season culprits or weather animals. This one is the most common. We call it the ordinary or air mass thunderstorm. And we call it an air mass thunderstorm because it's primarily driven by a warm and humid air mass brought in from the Bermuda High. This is the most common warm season or summertime rain-making event that you and I see in western North Carolina. We've got distinctly different stages, and this is covering all three stages. You see the names underneath the panels. This entire lifespan or life cycle of this single entity is less than an hour. You can go from blue sky to roaring thunderstorm to nothing in less than an hour, which is pretty impressive. What that implies then is that this type of thunderstorm generally is not around long enough to get into any trouble. The longer a thunderstorm or summertime event can be around, the greater the chances that potentially dangerous things could happen. I tell my students it's like if you've got a niece or a nephew and you leave them playing in the room quietly by themselves, the longer they're in that room, the longer the chances that something undesirable is going to happen in that room. So I liken these thunderstorms to our young nieces and nephews. The next level of sophistication and longer lifespan is what we call a multi-cell thunderstorm. This is possible when the wind structure, that vertical wind structure was kind of highlighted here to the left-hand side of the picture, contains a pretty moderate amount of change in wind speed and direction with height. And that's something we call wind shear. So when we go from a very low wind shear scenario to a moderate wind shear scenario, then we have the possibility of multi-cell thunderstorms. And so these can definitely last longer than an hour. These are probably the most common disruptive types of summertime thunderstorms that we see here in western North Carolina. The third kind, the kind that gets all the press, if you've ever seen the movie Twister or Twisters, this is the one that gets all the attention. This is less common for us here in western North Carolina, but we do see supercells every once in a while, and I will show you some examples here in a little bit. Out of all the three different thunderstorm types, this one is possible when we have extreme or very strong vertical wind shear, and so that allows for the maintenance of that structure right in the middle that's called the mesocyclone. And every once in a while, that mesocyclone and the downdrafts on the outskirts of the mesocyclone combine in a favorable way, which we're still trying to understand, to produce a tornado. So in terms of summertime convection, the supercell thunderstorm is the most likely to produce tornadoes. However, even the percentage of supercells that produce tornadoes is exceedingly small. It's easily under 5%. So tornadoes in and of themselves are very rare events. Let's review some topography, because this is going to play a significant role in terms of when things are worse or better, because these are the things that can contribute in either category. So, of course, one of the things that we have to keep in mind is that from a meteorological perspective, we here in the French Broad River Valley are in a relatively uninteresting part of western North Carolina if you happen to be a weather or climate specialist. And we'll talk about why that is. And, you know, there's a reason why the Biltmore House was built where it was. And we were talking even about the NOAA presence here in Asheville. It was brought here way back when because it was decided that Asheville was protected or shielded from some of the worst weather, which is, of course, ironic based on what happened a year ago. But so there is this general sense that in terms of a climatological perspective, you know, the French Broad River Valley and being in the middle of the mountains seems to provide some protection. Unfortunately, that has also provided in some myths, and we'll talk about dispelling at least one of those myths here before the end of the talk. So before we got one more slide related to topography, and that's just general geologic terminology. We here in Asheville are a good distance away from the Blue Ridge Escarpment. That's what the BRE stands for. The Blue Ridge Escarpment is really where, if you're a weather fan, you want to be hanging out along the Blue Ridge Escarpment, because that's where really interesting things can happen. But we here in the French Broad River Valley are far enough away from it that its impacts don't get us directly. They may get us indirectly, as we saw with Helene a year ago. And then the other feature is the Brevard Fault Zone. You've probably been seeing in social media that we've been getting, it seems like recently, a fair number of earthquake reports. Nothing on California scale, certainly, but you know, perhaps enough to rattle some cabinet doors or whatever. So we'll keep these in mind, both the basic weather animals that we see here in western North Carolina and the geologic formations, to understand a little bit of what's about to be described. So before I do that, is there anything that I need to clarify or straighten out? Any questions to this point? So let's start first with how mountains can actually help make our lives less complicated. And that's just a nice way of saying less dangerous, right? So one of the features are something that we describe. I just talked about it actually last week in class, this concept of rain shadows. So one side of the mountain is where you get most of the time the winds in a direction that's causing uplift. And anytime you move humid air up, it's going to be converted into cloud and potentially also precipitation. So on this picture, you could kind of think of this as maybe on the left-hand side is Knoxville, and the right-hand side would be Asheville. So Asheville is, from a climatological perspective, in a rain shadow. We tend to be on what's called the leeward side. That's where the winds are actually coming down the mountain. And so that tends to reduce our amount of precipitation in general. And it also, if you compare the temperatures on the Knoxville side and the Asheville side, that air coming down the mountain, if it's created clouds on the Knoxville side, that air can actually be warmer by the time it makes its way down the mountain to the Asheville side. In fact, you can see this in the numbers in terms of climatology. Asheville, in a normal year, gets about 46 inches of rain per year. In contrast to that, down near Brevard, Lake Toxaway is easily twice that amount. And again, that's because Lake Toxaway in the summertime tends to be on the windward side with that southerly flow. And then as that flow goes over the mountains between Brevard and Asheville, all that moisture gets converted to clouds and rain far to the southwest of us in Asheville. And then by the time that air comes down the mountains into our valley, there's very little chance to get as much precipitation. And so this is a very real rain shadow effect. Now, of course, this doesn't help your gardens, right? So maybe it's not necessarily a positive thing, but at least it's an explanation for why things are so different down in Brevard compared to what they are here in Asheville. Now let's get into what sometimes, or I should say most of the time, happens when these potentially dramatic warm season thunderstorms encounter the mountains. So here's a little cartoon that's depicting a pretty strong squall line. That's considered a multicell, right? That's the middle or moderate type of thunderstorm as it encounters the mountains. And so you can see when it's over on the Knoxville side, that looks pretty intense, pretty ominous. We'll see a radar example here pretty soon. But then as it's forced up and over the mountain, the fact that everything in the air has to be lifted creates or requires work to get that done. And sometimes that work then is using up energy that would go to bad things like strong winds or heavy rain or big hail, and instead has to go into literally kind of lifting the air up and over the mountains. Also notice in the bottom diagram, which I'll enlarge here, that the mountains sometimes cause a pause in the thunderstorm, and then it regenerates over the Blue Ridge Escarpment. So this picture is showing you kind of the dying system to the west and the genesis of the next new system that's really down on the escarpment. So this is why your friends or your family who live down in Hickory and places east of Hickory, that's why they tend to get slammed pretty well with these thunderstorms, and we may not see much. I mean, we might get rain out of it, maybe a little bit of lightning, but that doesn't make it a severe thunderstorm. Statistically, that's backed up with research. So notice that only about 10 to 30% of convective episodes were able to survive as they went over the mountains. So again, this is looking at squall lines, multi-cell thunderstorms. So if you're a betting person, if you wanted to say something's not going to happen, you'd put money, 90 to 70%, you'd be correct. So the mountains do, in general, protect us from a lot of these events. But notice it's not 0%, so it's not protecting us from all events. So here's an example, squall line. Way back, I call it warm season. Sometimes we get warm season structures in the technical winter month. This one was from back in February 2011. 2011 was an incredible year for weather, by the way. So this is what the weather map looked like. Squall lines typically happen out in what we call the warm air, the warm sector. So it's usually out ahead by about maybe 100 or 50 to 100 miles ahead of the cold front. And so let's take a look at a radar loop here. Well, first of all, these are reports of severe outcomes, but it's entirely on the Tennessee side. So you can see the counties. There's Unicoi, Knox County, both of them related to primarily wind, strong winds, and wind gusts in the upper report as high as 90 miles per hour. That's going to cause some structural damage. Down at the bottom, again, is just talking about thunderstorm winds, and again, down in Knox County, gusts up to 63 miles per hour. A thunderstorm qualifies as a severe thunderstorm if the wind gusts exceed 58 miles per hour. So both of these reports qualify this squall line as severe on the Tennessee side. But now we're going to watch what happens when we cut across the mountains. So we'll go through this a couple times. First of all, let me highlight the yellow line there. That is a severe thunderstorm watch boundary, and it's meant to say anything at or east of that yellow boundary is a potentially severe thunderstorm. So here's the squall line coming in. You see a bunch of polygons that the Weather Service office is trying to warn people about. And notice that the red colors, the red shading, tends to disappear as it comes across the mountains. And so this was that exact same event where all those wind damage reports came from the other side of the mountains, the Knoxville side, and there were no damaging wind reports from the Asheville side or any locations east of the mountains. So here's one of those most likely events, right? 90 to 70%, where the mountains actually do disrupt the structure of this squall line enough that it is not able to maintain its intensity as it comes across the mountains. So any questions before we depart talking about squall lines, multi-cell thunderstorms? Of course, yes, question.
Can you repeat what that yellow line represents?
Yes. So we have a NOAA facility out in Norman, Oklahoma called the Storm Prediction Center. And every day they're looking for regions where severe thunderstorms are possible and where tornadoes are possible. And so when they identify an area, they put out a polygon. And so they're the entity that put out that yellow line that's part of a polygon. I don't have a broad enough view to help you see where exactly it covers. But the rest of the boundary goes kind of to the east. And so everything at and to the east of that yellow boundary is where they thought the conditions were right for a severe thunderstorm. Now, as that thing is rolling through, you see some other polygons pop up. Some of the smaller yellow polygons are the local weather service, after looking at radar or getting reports from state troopers or emergency managers, they'll put out a severe thunderstorm warning. So the smaller yellow polygons are severe thunderstorm warning. However, you also might see a bunch of green polygons. Those are put out by the Weather Service warning about flash flooding occurring. So they have different colored polygons that the Weather Service puts out according to what the threat is. If it's a tornado, it will be a small red polygon. But the large polygon that we see at the beginning, that's put out by the Storm Prediction Center based out of Norman, Oklahoma.
So it seems almost counterintuitive to me, but the squall line looks much more well-developed west of that yellow line, but you're saying that the potential for tornadoes and other activity is greater east of that line.
Actually, I think you're right. I think it's west of that line is where the larger polygon was, and then they knew that the mountains were going to be weakening it. Yeah.
Please help me. What is a polygon?
A polygon is a squashed square or rectangle. It's basically a multi-sided. It doesn't have to be four-sided.
I mean, I sort of understood that, but you talk about all these polygons
Yes.
in terms of what it means, and it's not something I guess I feel like I understand.
Sure. So kind of leading out in front, you see these various shaped polygons. Those are being put out as things go through by the local weather service office. So I see some green right there. There's some yellow. It's hard to see the colors with the thing in the background. There's some green back in there. And there's green right there. There's a red one for tornado right there. So they're kind of following the feature along as the local weather service office is recognizing that the structures in the radar seem to suggest that either a lot of rain or a lot of wind or even damaging hail might be happening underneath those very bright orange features in the radar. So I don't know if that's helpful. They're not easy to see because they're superimposed on the color of the passing squall line. Yes.
Where is Asheville on that map as it goes through?
Okay. Asheville's right in the middle of this county. There's Buncombe County right there. So if I leave that right there, you can see it really falls apart. And all we got out of it here in Asheville was rain, maybe a little bit of heavy rain for a very brief period. Yeah. Right, so trying to communicate the threat is certainly a huge challenge, and colored polygons is one way that they do it. They try to send out, if you subscribe to their texts, they can send out warnings like an Amber Alert. If they see your phone within one of those polygons, you will get a loud siren like an Amber Alert that tells you severe thunderstorm warning. So it is possible to get that on your phone, but the cell towers have to be working and your phone has to be on, or the volume at least has to be on, right? Any other questions before we move into the other more dramatic, the type of thunderstorm that receives more press coverage and is the subject of those two movies I mentioned? So supercells, these are of course the ones that out of all the thunderstorm types tend to be the ones that could have the most likely chance to produce a tornado. And I'm basically quoting everything from a study that was done from colleagues at UNC Charlotte. And so they looked at some backgrounds that make it more likely or less likely for supercells to make their way across the mountains. And these two cartoons are kind of showing you that supercells generally happen in the warm part of our large-scale cyclones that I talked about, the warm sector. But quite often in the environment of that warm sector, you can get a low-level jet that can help or hinder these supercells trying to cut across the mountains. So their findings were that the orientation of that jet stream that's feeding these supercell thunderstorms is really critical relative to the mountains. So when the jet, at the lower level at least, is parallel to the mountains, these supercells are more likely to have a continuous feed of fuel that actually gives them the better chance to get over the mountains. If the upper level jet is located pointing more across the mountains, then it's unlikely that these supercells, which require humid air continuously, ingesting that to maintain their strength, they're not going to make their way across the mountains. So let's look at some stats. So supercells, of all the supercells that are made, only about 1/3 of them make their way across the mountains, or are able to survive. Now I mentioned 2011 as being a dream for weather fans. In April, you may remember if you were here, April 27th, April 28th, there were numerous supercells. That was the infamous day of the Tuscaloosa supercell tornado that literally damaged part of University of Alabama. That supercell on the 27th touchdown, a tornado touchdown right around rush hour, 5 o'clock Central Time. That supercell maintained its identity all the way into the French Broad River Valley. And so I didn't sleep much that night because I was watching that thing the whole way. It rolled in town here about 11:30 p.m. that night. Thankfully, it did not drop a tornado. However, if you all remember, there were other supercells, and some of them did drop tornadoes in the southern end of the Great Smoky Mountain National Park. So one myth that I want to make clear here is mountains do not protect us from tornadoes. And I'll give a specific example of when they actually made things worse, but that's for the other part of the talk coming up. So only 1 in 3 supercells make their way across the mountains, and supercells are already a very rare entity or weather animal here in western North Carolina. So chances are, if you're going to have a tornado cause problems, it's not going to be from a supercell. It actually is probably more likely to be a squall line, which is more common. And then even given the odds, it's more likely that they'll produce a thunderstorm or a tornado that causes some damage here in western North Carolina. All right, now we are going to talk about when the mountains make things more challenging or more complicated. And we'll start with the warm season because that's what we're just finishing up, and then we'll get into forward-looking over these next several months coming up. What do we need to be watching for? So one of the things that's a true fact just about every day in the summer is that the mountains are a local heat source. Anytime you warm the atmosphere from underneath, you are destabilizing it. And when that sun hits that side of that mountain, that's going to create a local hotspot, And as this picture is showing you, when you've got heating happening on both sides of the mountain, that's going to create what we call convergence zone, and that's going to force rising motion to come together up at the very top of that mountain. And so just from a general day-to-day perspective in the summertime, the fact that the mountains are consistently a heat source means that the tops of those mountains, those ridge lines, are more likely to get precipitation. We have a rain gauge network in Haywood County, and the most rainfall of all 32 gauges in Haywood County is located right at top of Hemphill Bald. If you've ever been on the Cataloochee Divide, that's the peak, the tallest peak, from which if you stand up there, you can see Ski Cataloochee just across to the other isolated peak. But Hemphill Bald being on the ridge line, a local high spot, that is a bad spot for thunderstorms, or a good spot. Bad for me when I'm out there with students in the summertime. We try to get through there as quickly as we can. So we're going to look at a multi-cell thunderstorm example. This is not a squall line. This is a different kind of multi-cell example. But this happened back in our gauge network in Haywood County in July 2011. For those of you who've been around here and were here at that time, this is the event that caused a huge amount of water to come down the mountains and basically washed out the fish hatchery on the reservation, the Cherokee Reservation. They have a trout hatchery, and this event caused so much water to come down the mountain that it basically completely scoured out everything that was in their hatchery tanks. So we're going to watch a thunderstorm progression, and I'm going to run this a couple times because it goes by kind of fast. This whole thing happened right on the boundary of Swain County and Haywood County. And notice there is that polygon that happens at the end. There were two different distinct types of multi-cell thunderstorms that rolled through the exact same area. If you are familiar with Soco Gap, as you come through Maggie Valley, that's kind of right in the middle of where these thunderstorms were rolling through. And so I know in talking with the locals over there that Soco Gap does tend to be a really good place to generate thunderstorms. And that's, again, this kind of ridge line that the Blue Ridge Parkway kind of follows as it's going through until it gets into Econo-Lofty. So you have two phases. You've got what I call the trail blazer that's following the ridge line at the early part of the loop. There it is right there. And then right behind it, not very long after, is what I call the trail wrecker. And eventually they both merged. And this happened from 8 p.m. to midnight, going from the 14th to the 15th. It was very fortunate, the timing of this, because if you've ever been on the reservation, that creek or river that goes right next to the hatchery is a very popular trout fishing area. And so if this had happened earlier in the evening, it's quite likely that there would have been people out there fishing for trout, and of course that would have been really bad. So the fact that this happened later in the night was probably the reason why there were no fatalities out of this event. And you can see there's two things going on, right? You've got that, there's that polygon saying flash flooding near Morristown, and then you've got the polygon that's directly linked to what we're talking about along the boundary of Haywood County and Swain County. So if I look at, we have two rain gauges that were in the perfect spot to observe what was going on. So here's some times that are highlighted. There's 8 p.m. Eastern time here, 10 p.m., and then there's midnight right there. And so these are accumulations of rain. Unfortunately, being a scientist, these are in millimeters. But if you think about 25 millimeters is about an inch. But I've done the math for us, so we don't have to figure it out. Two rain gauges, basically almost 5 inches of rain in maybe 3 to 4 hour periods. So that's over an inch an hour, which is a really intense rainfall amount. And so all of that water basically caused things that sound very familiar in light of what we experienced with Helene. The Gunter Forks Trail had 3 distinct debris flows that were triggered by all of that rain. So there's 1, 2, 3. Here's a picture of one of them. And that trail was closed for a very long time because they had to try to fix it. And it's not easy to fix a trail that's in the middle of nowhere. You have limited resources. So a seemingly innocent-looking thunderstorm having multiple or multi-cells go over the same area, dumping 5 inches of rain to 3 to 4 hours, is going to cause some real problems. And this is in the middle of nowhere. When landslides are triggered in what they call modified slopes, anytime there's any cut to the side of the mountain, whether it's a road or a culvert or whatever, that introduces increased likelihood of landslides and debris flows. And right now the count with Helene is just over 2,000, and a significant number of those were triggered near modified slopes. Oh, question?
I look at that radar, and there's nothing that looks unusual to me as far as, oh, this is going to be 5 inches in 3 hours of rain. It
Yes.
doesn't even have the darkest colors of the radar spectrum.
Yeah, you're exactly right. And so the Weather Service office should be commended just for putting that polygon out there. Our rain gauges don't report in real time. We had to go out there and get that data, months later. So they have specialists, radar specialists, who are trained to watch, and when they see a certain color kind of hanging out in one area, then they're probably going to put that polygon out there. They tend to put it out there maybe more than they really should, just to give that warning out to people that something may be coming your way. So they have to verify these things. This one verified pretty easily by looking at the debris flows when the Geological Service went out there, and then what happened at the hatchery made it pretty obvious too. So yeah, that's a very good point. And I just gave a talk a few weeks ago. We had a landslide workshop here, and I said my talk was primarily on things that are common that can be seemingly innocent looking because they're common, but yet if you get the timing of things happening in a unusual way, you can have trouble happen. And so you're right. When I look at that, I'm looking at the thing to the north, right? That's where bad stuff is happening. And so this is a huge challenge. And of course, this is in the middle of the national park where you have no people calling in, helping you that something bad is happening. So they're literally working blind in a big chunk of these parts of the national forest and national park. It's a challenge, absolutely. Oh, yeah.
Is the NOAA office still open?
Yes, they are. They are doing their best. I'll just leave it at that. Yes. So let's move to the atmospheric river example. And of course, I mentioned that that's most common in our winter cyclones. And of course, now I'm going to talk about an example that happened on the 4th of July back in 2013. 2013 was another one of those unusual years for our rain gauge network. That was the one that had the most rainfall up until 2018 happened. So we had some winter-looking like storms that were very large in scale that rolled through in June and July of that summer in 2013. And one in particular that we're going to talk about here is a good illustration of what happens when an atmospheric river encounters the mountains. So California has their atmospheric rivers, we do too. And this one was unusual just because it happened in the month of July. So here's the analysis. And I don't want to criticize, but this is a very unusual analysis and is probably not correct. But at least this boundary here is showing that there's really humid, warm air here over North Carolina to its east. And so that at least points you out to one of the important ingredients. And here is the radar. And again, remember the green polygons are the Weather Service saying flash flooding is happening, or it's about to happen, it's imminent. You can see almost the entire of western North Carolina is under some green polygon. This actually looks a lot in terms of the polygons of the coverage of what happened with Helene rolling through. At some point, almost exactly a year ago, right, almost just after noon on the Friday, 2024, we had the entire western North Carolina in polygons. So this is not a tropical system. This is a mid-latitude storm with that warm conveyor belt having an atmospheric river attached to it, and that humid air is being brought up the escarpment and up the mountains and producing an incredible amount of rainfall. So it is the most common problem out in California, but we do get 1 or 2 events in the winter, every winter here, that can cause some serious issues. And in fact, when we get these atmospheric rivers, other than tropical systems, these storms that having atmospheric rivers, they are the most responsible for non-tropical based landslides. So we do get landslides out of these more wintertime events. So fortunately or unfortunately, we're going to look at our rain gauge observations from along Cataloochee Divide. That's where all those points are located. It doesn't really matter exactly where they are. We're going to intercompare. And again, we've got a period, relatively brief period, as that atmospheric river is encountering the mountains, where the total accumulated rainfall varies from almost 3.5 inches up to just over 5 inches. That 5 inches of rain was not actually Hemphill Bald. It's the one way down here where there is a valley. When the winds are from the right direction, that has a valley and then a wall right behind it. So all that moisture is brought into the valley and then is forced up. And that rain gauge is, if you know where Pinnacle Ridge is, that's where this rain gauge is. And it's got a unique geometry that if you get southerly humid air going in there, you are going to get a lot of rain. And that's exactly what happened when this atmospheric river went through in July of 2013. Let's look at a supercell example. This one is relatively recent. And some of you may remember the tornado that touched down in Black Mountain. That was a few days before this. This one actually encountered the mountains to our west and caused some serious problems for the counties west of Buncombe County. So just for a point of reference, here's us in Asheville, there's Buncombe County. And notice this is the Storm Prediction Center again saying the atmospheric conditions are favorable for the possibility of tornadoes west of Buncombe County, and they ended up being right on. So I'll point where we are in Asheville, and these are supercell signatures coming through. You can see a red polygon that was put in as a tornado warning for eastern Buncombe and western McDowell County. But the really serious stuff happened to our west and southwest, down in these counties down here. So here's the Storm Prediction Center's red boundary, and then you see all kinds of smaller boundaries, polygons being put in by the local weather service offices. So here's an example, that minority where the supercell actually was able to maintain its strength and roll across the mountains and drop a tornado, or 2 actually. But we're going to focus just on one of the tornadoes. These are the overall storm reports from those supercells going through. And you can see the color scheme down here. Anything red is a tornado report. There were 74 on this day. Wind is strong winds exceeding 58 miles per hour is blue. Hail, large hail reports. We tend to not get large hail around here. It tends to be mostly wind or tornadoes. So anytime the Weather Service puts out a warning, they have to go do a survey. And they went out. Glenville, there's a Glenville Lake. We like to take our kayak out there and go paddling around. So this went right past Glenville Lake and lasted for quite a long time. You can see the time up here. This is about 10 minutes. That's pretty long for a tornado to be on the ground in the mountains. The impressive thing here is the tornado scale. Tornado ratings, if it's an EF0, that's relatively weak tornado. An EF5 is the kind that you get out of the supercells that you see happening in Oklahoma. An EF2 is definitely on the strong side for us here in western North Carolina. And you can kind of visualize or see that when you look at the tree damage from that tornado rolling through the national forest. My colleague, Professor Chris Godfrey, is funded to study tornadoes by looking at the tree damage as those tornadoes go through forests. You can learn a lot about the tornado funnel structure by the damage pattern left behind as it goes through a forest. So EF2 is very unusual in western North Carolina. All right, any questions on warm season stuff before we talk about bad things happening in the winter, which of course is coming up? So the first scenario, as I mentioned at the very beginning, I moved here in 2004, and so I've seen what I would call wimpy ice storms, but I know that some pretty serious ice storms are possible here in Western North Carolina, so I'm going to explain kind of the setting to make that possible. And the most common thing to happen is to have that high pressure system kind of up in southeastern Canada, just north of Maine. And the circulation around high pressure systems is clockwise. And so that brings in some pretty chilly air that spends its time either over the snow-covered part of Canada or goes over the Labrador Current, which is pretty chilly. And as that air makes its way in, it encounters the wall of rocks known as the Appalachian Mountains. And as I mentioned, it takes a fair amount of energy to get that heavy air up over the mountains. And so it doesn't go up and over the mountains. It stays on the east side. But instead of going up and over the mountains, it gets forced to the south. And sometimes that cold air can make its way all the way into the French Broad River Valley. And so here's a little cartoon. I've shaded in where that cold air is. And so that's because there's that high pressure system way over here to the north, northeast. And that cold air then encounters the mountains and then is forced to the south. So this is really cold air. And how cold is it? Well, it's below freezing temperatures. If you happen to get one of those winter storms moving in at the time of what we call cold air damming, don't bleep that out, Kent. That's not a swear word. It's damming as in a water dam, right? The rocks are literally acting as a dam, preventing that cold air from moving on the other side of the mountains. And so when you get humid air forced up above that cold air, you can get the optimal conditions to have a bad ice storm. So here's a little schematic. We create snow here. This is about 3 kilometers above the ground. And when it encounters a layer of air that's above freezing, that snow is going to melt. And then as that melted liquid goes through the sub-freezing air, it may or it may not freeze, depending on the depth of that cold air. Liquid water does not spontaneously freeze unless the temperature gets down to minus 40 degrees Celsius. So chances are that it's not going to have enough time to refreeze. If it does, then it reaches the ground as what we call sleet or ice pellets. Those are the things that you can hear and see bouncing off of your window or your car. So it's very much a sensory experience. However, when it's freezing rain, that's altogether a different scenario. So the water falls and becomes super cooled because it's not ice yet, it's liquid, but it's liquid at a temperature below freezing. The minute that super cooled water hits a frozen object, it freezes on contact. This is why before you take a flight in the airplane in the wintertime, you see all those people out there spraying icing chemicals. It's because if they fly through, and they probably will, fly through super cooled droplets, they're going to freeze on the wing on contact. And if you get enough accumulation, that's going to change the shape of the wing and you lose the lift, and that's not good. For us, right, yeah. Let's focus on the ground, right? For us, freezing rain actually can be a bit of a surprise because you can't really tell. You can't hear it because it's liquid, and it doesn't make a noise when it freezes. So my one experience, bad experience with freezing rain, was I thought it was liquid rain. I went out to take the garbage can out to the driveway, and my feet just went out from under me. Fortunately, I didn't hit my head on the cement, but you just can't tell, right? The only hint that you know something's up is if it begins to accumulate enough that you start hearing the cracking of the tree branches. That's when you know, okay, this might get bad if it doesn't end soon. And of course, if it's going to accumulate on tree branches, it accumulates on power lines, and if it gets thick enough, the power lines are going to just give way. So this is a scenario that would not be possible here were it not for the mountains acting as a dam, keeping the cold air in place in western North Carolina. So we'll look at an example from January 2013. When we get an interesting weather storm. We are literally out here in the parking lot launching weather balloons. So snow, freezing rain, sleet, we're going to be out there launching weather balloons. And this happens to be the observations from one of our weather balloon launches back on January 25th. And so I've highlighted on this diagram the freezing line. That's the temperature line that's below freezing to the left, above freezing to the right. And so here, these being close together, there's snow being made in the cloud up here, and as that drop falls through, or that snowflake falls through, when it reaches this altitude, it starts dropping into that warm layer of air. It melts, and then it comes down closer to the ground into the air that's cold, and that's an event where we had freezing rain. Now, it wasn't a long event, and so it didn't cause power outages, but we were able to capture the exact time when the freezing rain event had happened. Now, for us, our students and I, usually we're doing this because we're hoping for a really good snowstorm. Unfortunately, when that warm air comes in, it changes things over from snow into sleet and freezing rain. And so it's kind of disappointing. I mean, it's cool from a science perspective to be able to capture this, but anytime you get sleet or freezing rain, that's taking away from your snow accumulation. And we want snow, right? We don't want sleet or freezing rain. But from a science perspective, it's very interesting to see how this complex, large-scale storm is creating some very interesting localized effects. We can see this when we send up a laser. This is kind of like radar. And so the higher the colors, the stronger the backscatter. And you can see where there's the higher numbers, or the more yellow turning to red, that's where we're getting more return energy. And what that means then is it's going from snow to liquid. So this area right here is highlighting the melting altitude, right about 6 kilometers. So snow up here, not much reflectivity, not much energy backscatter. It melts, becomes liquid, or at least water covering the snow, and that's highly reflective at these wavelengths, so we get a lot of energy return there. And then by the time it makes its way down here, it's entirely liquid, which isn't as reflective. We can also look at the speeds. Snow falling nice and slow, right, because of the updraft in the cloud. But once it melts and becomes entirely liquid, it starts falling much faster. And so this is another way of highlighting where we're looking at snow that falls more slowly compared to where we're looking at pure raindrops, or maybe even supercooled liquid rain. One final example, and then we'll open it up to talking about whatever you want to talk about. And this is related to a very common event known as northwest flow snow. This would not be possible at all were it not for the mountains, and I'll explain why that is in a minute. We're going to look at a classic case, a pretty impressive case, when we were doing weather balloon launches up in Avery County. But the setting for a classic northwest flow event is you've got a low pressure system that's located up in the northeast somewhere. And so what that forces then is that cold Canadian air dropping down into the eastern US, and of course the wind direction is from the northwest. And so that's why we call this northwest flow snow. Well, if the mountains were not here, all we would get would be nice, cold, windy, blustery conditions, and that would be our weather. However, because we have mountains, the mountains cause some interesting things to happen that we'll talk about. This is the middle part of the atmosphere. This deep feature here is what we call a trough. And underneath the trough is almost always some pretty cold air. So for the trough to be this deep, there has to be some stinking cold air coming through behind it. And what I mean stinking cold, I mean, getting down to the teens, single digits in Fahrenheit here in Western North Carolina. So here's that same thing that we used to look at the freezing rain event. This is showing us the cloud tops. This is a really interesting event, these northwest flow events. The top of the cloud is no more than maybe a couple miles above the Earth's surface. Very shallow. They're in the layer of the atmosphere we call the boundary layer atmosphere, and it's really close to the ground. There's 2.5 kilometers, right? Down here is the showing us kind of the snow that's falling out of these clouds. So the air is very cold. However, somehow it's very efficient at making snow. And the reason that it happens is because you've got those mountains lifting a modest amount of water vapor up on the western side. And if we get the proper windy conditions, we're looking at the bands of snow, that those bands can extend well down the primary ridgeline along the Tennessee-North Carolina border. So when you and I feel northwest flow here in Asheville, we know that the winds have got to be pretty strong and rip-roaring to form these bands that can extend beyond the primary ridgeline of the Appalachian Mountains. So the mountains provide, again, that lift of that relatively humid air that gets converted into snow. Now, this is the kind of snow that you and I can deal with. Because the temperatures are so cold, we call it a dry snow. Dry snow is very feathery. It's powdery snow for those of you who like skiing. Powder skiing is the best because it's effortless. It's not very heavy, doesn't have a whole lot of water to it, and so you can carve through it pretty easily. Shoveling, not as heavy as the wet stuff. So when we start getting these temperatures that are 20 degrees, 15 degrees, you get this dry snow that makes for a pretty good accumulation, but not a whole lot of liquid content in that snow. So powder snow, good stuff. So let's summarize, and then we can take more questions or talk about what's looming, right? So mountains make our lives less complicated generally when we are on the downward or leeward side of the mountains, as Asheville is. When our large-scale weather patterns are relatively weak. And if our large-scale weather patterns are relatively weak, then the mountains are entirely responsible for creating lift and creating clouds. So again, it takes effort to get those air parcels lifted, and nature generally is not going to want to put in the work. So when does life get more complicated? It tends to be when we are on the windward side, because we are then on the side where that humid air is being lifted up the mountains. That's being converted into clouds and precipitation. And then the worst scenario is when the large-scale weather patterns work together with the local weather patterns to keep the fuel going to make these a longer-term event. And of course, anytime the niece or the nephew's alone in the room, the longer they're there, the greater the chance of bad things coming out as outcomes. So I just want to acknowledge a few people who've helped us through the years, and I'll open up to questions related to this, and then we can spend a little bit of time talking about what's looking like things are going to be happening here pretty soon. Yes?
Would you help me understand barometric pressure, its impact on weather, and does it have impact on human bodies?
Let me answer the last question first. Absolutely. And I asked a friend of mine who's a physical therapist about how is it that air pressure impacts the human body so strongly. And she said the tolerances within our joints, within our body, are so small that any slight deviation from our normal shape, whether it's bone or whether it's muscle, can cause discomfort. And air pressure is enough that it can cause a slight deformation, whether it's in bone or whether it's in ligament or whatever, that we exceed that tolerance and then we start feeling it in our joints. So there is a very real physiological reason on why changing pressure in particular causes these aches and pains. So absolutely, that's very true. What was your first question was?
What is barometric pressure, and what is it? How do you interpret its impact on weather?
So these lines that are on this plot are lines connecting the same barometric pressure. So when you see the L at the very top up near Maine, that means there's relatively low barometric pressure. And yeah, out west, you see all those blue H's, that means relatively high barometric pressure. Those are nothing more than how much mass of the atmosphere is above that point. So if there are fewer air molecules over a location, that's where you'll get low pressure. where there's a larger number of air molecules overhead, that's where you'll get high pressure. So high pressure and low pressure are not all that impactful on their own. It's when you go through the change. Like, look at the low is up here near Maine. As we go west of that low, look at how rapidly those lines are changing. That's what we call a pressure gradient. And I should say a strong pressure gradient. When those lines are close together, it's a strong pressure gradient, and that is going to force very strong winds. So it's the change in pressure in terms of the weather world that we're really watching for. We're watching for how much is the pressure going to change over this period of time. And if it's a very rapid change of pressure, we know the winds are going to be very strong. So for the tropical systems, the center is a very low pressure, and then not very far out of the center of the tropical systems, it's relatively high pressure. And so there's a very rapid change in pressure, and that's why we get such strong winds in our tropical cyclones.
When I look at the weather app on my phone, it often doesn't agree with what I'm seeing out the window. Where is that information coming from? Is it somewhere far from where I am? Or?
The answer is it most likely is coming from somewhere far from where you are. First of all, we will never be able to answer that question unless we're a part of that company that's developing that app. They won't want to disclose it. Yes, especially being in the mountains, you can have an appreciation for the fact that things change fairly rapidly over a fairly short distance. And so there's probably not going to be any app that will give you a satisfactory condition at the location you're at. I mean, the difficult part about being a forecaster is we don't have observations everywhere where we need to have them. And so what I tell my wife constantly, and she's probably sick of me saying this, don't look at your weather app, go look at what the Weather Service forecast is. And they have a very easy point and click web page. I don't think they're allowed to have an app because that would be threatening the private interests. So they're not allowed to have it. But in terms of forecasts, they have forecasters who have been in that area for a long period of time, and they understand the microclimates. The apps are all AI generated. Probably no human is in the loop at all. And so you're getting entirely what's coming from a computer processing job rather than any human interaction.
Yes, back in 2009, I live in West Asheville, and there was an unusual event. It appeared to be there were fairly widespread outages of stoplights and things like that. But there was a line. It seemed to go from northwest to southeast, and it took down a whole lot of trees. It went right beside our house and took down a 100-year-old locust and a 200-year-old oak tree on Louisiana Avenue. And every tree was laid down in the same direction. There was no cross. Every tree, you could just see this straight line. And we were calling it a downdraft. And is there such, I mean, there seems to be. I saw it with my own eyes, but I've never heard of these downdrafts, and it had to be a very, very powerful wind.
Yes. So when, and what you described is exactly what the Weather Service is looking for when they go out to do a storm survey. If it's something they call straight line winds, all the trees are falling in the same direction. When it's a tornado, there is a circular kind of swirl pattern. So it's like, you know, your favorite crime TV show. There's things that you pick up at the crime scene that kind of tell you what happened. Well, it's the exact same thing when you go out to an area that was impacted by a weather event. So I brought this back up again. If you've got a fairly long line of straight line winds, chances are it was a squall line that went through. And if we go back to the original structure in my little cartoon starting off, sometimes if we imagine this multi-cell thunderstorm extending into the board and out of the board into a constant line, so it's a squall line, we sometimes get this thing called a low-level jet that comes into the back end, and in this downdraft, that very fast-moving air gets caught in a downdraft and then forced down to the surface. And that can happen along the entire line. And so that's how you get a very long line of trees blown down that are all in the same direction. I'm guessing it was probably a squall line with this, what's called a rear inflow jet that is brought down to the surface. Yeah, you're welcome.
In the slide that you showed of the laser report, I'm having trouble visualizing how that data is collected, because when I think of a laser, like your pointer, you've got a very, very small area.
Yes.
So when you showed that slide, which was more of a table,
Right.
I'm
Yeah.
just curious to try and visualize how that data is collected.
Yeah. So what we're looking at on the x-axis, that's a great question. The x-axis is time. So we send a pulse up every 15 seconds, and then we stitch those together. And so that's what we're looking at both with this slide and the next slide, is multiple pulses that we send out there and then stitching them together. So this is called a time height section, where time is marching. Here's the 1200, there's 1500. So time is along this axis, and then elevation is on the y-axis.
And each pulse over that time over the x-axis is from the very same sensor in
Exactly.
one position? And is
Yeah.
it shooting directly upward, or is it directly?
It's shooting directly upward, and it's moving at the speed of light. So, given these distances, it doesn't take much time for it to hit against the target and come right back.
Thank you so
Yeah.
much.
Thank you for asking for clarification. Yeah.
How do the mountains factor into the brown ocean effect? And is there kind of a tunnel or a funnel that goes from the Gulf of Mexico up to us, like what happened in Helene? Do we expect more of the same in the future?
So I guess I need clarification. The brown ocean effect, you mean debris, or are you talking about more like toxic algae bloom kinds of things?
I understand the brown ocean effect is something was observed in 2011 by someone from NASA, and it has to do with hurricane hitting land. And it used to decline in power, but through the brown ocean effect, it can gain speed and power after hitting land.
Huh.
And because we had that day and a half prior,
Right.
Yeah.
Right.
did the mountains affect that? Either protect us or not?
Right. So, okay, I understand what you're saying. So, usually most hurricanes, when they would make landfall, they lose their source of fuel because they rely on humid air being drawn into them to keep them going. And so what you're saying is, if the ground has enough moisture that there could be water vapor that's brought in, and so that there's not much of a loss of intensity because it's taking water vapor through evaporation over the land. I would say that probably the mountains, it's probably more important what kind of soil is good at holding on to water that could provide the water vapor that's needed. And sometimes the mountains aren't necessarily very good at holding on to water for a long period of time, so they might not be so helpful, but I could imagine there are some places in the mountains where it is good, like wetlands, things like that. So I would say, first of all, I don't know, but I would guess that there could be areas where it would be beneficial or help keep the intensity level, but I don't know if it's over a broad enough area to overall have a net positive impact. Good question.
So I have a question. We have some potential for excitement in the Atlantic. About when do you predict we will have better information to tell us which of our bathtubs to fill and how much peanut butter to buy?
Okay, so that could be a good segue if no one has any other questions on the presentation, because so please hold that, put a sticky note on that, and we'll come back to that.
My question might be related to that, but it seems, I've lived here 10 years, and it seems like we're getting more warnings of severe weather. And I don't know if it's because there's better reporting or because we are having more severe weather in this area. So that's my question.
That's a good question. I think it's a combination of both that you suggested. Number one, our technology is always improving so that we can see into deeper parts of the atmosphere that we couldn't see before. And maybe more importantly, our oceanography colleagues are really investing heavily into new ways to observe the ocean. And what happens in the ocean has a very significant connection to what happens in the atmosphere. So, given that, we are also seeing unbelievable amounts of warming in the ocean temperatures. And so, of course, that feeds not only our tropical systems, but it also feeds our summer systems. I mean, as I mentioned, summertime, the Bermuda High brings that humid air up into our mountains. So if there is more humidity, more water vapor, then it makes sense that there would be more either summertime thunderstorms or fall hurricane things that are able to actually track and be more intense by the time they reach us. So I don't think it's our imaginations.
I have a question over here.
Oh, yes.
And you talked about weather balloons. Is it possible at some point for those who are interested to come out and see one of those weather balloons? I think you've done it in the past, but some of these people are new and haven't known about that.
Yeah, absolutely. We could arrange something. I mean, we're hoping to be able to do it again this winter. So we could, every time we get ready, we let Catherine know. So she'll be made aware of that. We are doing one for a class in November, but I don't remember off the top of my head which day it is. But that would be another potential opportunity. So I could let Catherine know when our class is going to be up here and we're going to do a launch, and just to make a general announcement. Yeah. All right, so I might, okay. Yeah.
Can you comment on the orographic effect of the Blue Ridge Escarpment on Hurricane Helene, and any insights you have about that?
Yes, and I have a lot of things to say about that. So what I'm willing to do is say I will talk about all aspects of Helene in another talk, if that would be something that you would like. Okay. Yes, we have been studying it, and so if you could carve that on the wall or something so we can remember it whenever I'm going to be here again, that's a great question that will lead the way in making that presentation. Yeah. So I'm going to go through a series of slides here. Hopefully that won't, it's combining with Zoom here, so I'm not sure if I'm going to be able to.
While he's looking for that, let me point out, Dr. Miller was scheduled to speak last fall, and then the hurricane hit. We weren't psychic when we did that scheduling, but I want you to know this is happening now, and it's even more interesting to us now because he's doing it after the hurricane. Okay.
Right. So what we're about to talk about isn't even officially an entity. It is a, let's see if I can. So this is a sequence of pictures taken from what's called our geostationary satellites. So they hang out at the same spot above the Earth. And this is our snapshots in the infrared window. So we're looking at the temperatures rather than the visible parts. And the cloud tops show up as being very cold, and then the surface is quite warm as the orange shading. And the entity that I'm about to talk about and that everyone is curious about is kind of still off the bottom right of this screen. So you can see generally it's suggestion down there with relatively cold clouds, but it's still quite disorganized. So thunderstorms can kind of mold together and start to create a tropical depression if they have enough time to kind of form a larger entity. And for that to happen, of course, they need fuel, which of course is provided by the warm underlying ocean, but they also have to have favorable environmental conditions. So the environment has to be relatively weak in wind shear. Remember, we talked about wind shear with those different thunderstorm types. And so it does take quite a bit of time to get all of that mass kind of put together in one big, I'll use the scientific term, blob. So forecasts right now are having a lot of uncertainty because the thing we're trying to discuss isn't even a well-organized entity. And so because of that, there is a lot of uncertainty right now about what it's going to do. Now, if you look at the National Hurricane Center, they're pretty certain that something's going to happen eventually, because this red shading implies that there's greater than 60% chance. In fact, if you click on that, they say 90% chance of formation in 7 days. So their hurricane models are saying, okay, it's disorganized now, but we're 90% certain that it's going to become organized. So they're looking at the environment that this thing is trying to form in and saying the wind shear is going to stay weak. The ocean temperatures, of course, will stay warm where it is, and it's going to eventually have time to get organized. The real question at this point is what is going to steer or guide this thing once it gets organized. So the map that I wanted to show here is really the first point in time where it looks like it becomes organized. This is Sunday morning at 9 a.m. So that's a lot of time between now and Sunday morning at 9 a.m. So between now and that time, we're going to be, not we, but NOAA is going to be sending out Hurricane Hunter aircraft. They're going to be dropping special sondes into this environment. Satellites, they'll probably be using special scans from the satellites. And then they're also going to be launching special weather balloons all along the southeast coast to try to pinpoint the structure of this atmosphere to better get into what's going to happen later on. So if this is Sunday morning, then what happens, and I'm going to hit the start button. Remember that this is just one model simulation. And I'll highlight, so here's this blob that's going through the Caribbean. And so watch, this is from this morning's model run. And all this is just kind of showing us the energy of those different thunderstorms that's trying to get together. And so once we start seeing one of these lines kind of circle around it, that's when it's gotten organized. This is Umberto out to the east. That plays in as well on this forecast. So here we're now getting into Sunday morning. Okay, there it is, organized. The feature that is important to watch is this trough over here, because how this trough moves and how it strengthens in time plays a role in how that Imelda eventually is going to track. Now this scenario, this model run was made this morning, and this, if this were to be true, it would be bad for us. Not as bad as Helene, but it would still be noticeable in that there would be a whole bunch of rain associated with that. So let's go back and talk about the different possibilities. The weather centers, like NOAA's Weather Center, they run a lot of different solutions to try to figure out what's going to happen. We're going backwards, by the way. And there's three possibilities of what's going to happen. So we just looked at scenario one. Scenario one is the worst scenario for us in terms of we're going to get a lot of rain. It's not going to be as much wind. We didn't have 2 days of solid rain leading up to this, which, by the way, it's crossing that coastline Monday night, Tuesday morning. So we're not going to have the 2 days solid of rain right before it's going to happen. So the soil is not going to be saturated, and at the same time, this is not going to be as strong a storm as what Helene was. Helene was a Cat 4. That's considered a major category hurricane. And this storm is not predicted to be that intense. So this is scenario one. Scenario two, which some of the other models suggest, is that this trough out west, this feature right here, is not going to link at all with Imelda, and Imelda is just going to spin offshore. So the people along the coastal zone will get some rain, and of course they'll get waves, significant waves coming in, riptides, things like that. But for us, solution number two has Imelda not merging with the trough that's coming in from the west and just basically spinning. And then solution number three is that Umberto actually is able to have some influence and pull Imelda, the Fujiwara effect you've probably been reading about, pull Imelda out to sea. And that scenario number 3, there would be the least likely impact in terms of the continental U.S. So at this time, all 3 scenarios are possible, and we probably won't know until this thing actually becomes an organized system by Sunday morning. So I would be making preparations, but don't, drain your bank account making the preparations, because there's 2 out of 3 solutions that may not impact us, so that we're going to have to worry about water and power. And I would say even water might be a thing to be concerned with because of the rain, but we might not lose power if the winds never get very strong.
You had some very interesting displays up there, and I would love to be able to see them myself, but I don't want to get down to the 25-digit, URL or whatever. Is there a Google search that will get us to things like those charts that we can kind of play around with and look for?
Yes, in fact, I have the links at the very end of this slideshow presentation. So Kent has got a copy of that, and I'll make sure that there's a copy here so that you can get those later slides and find where these links are. Yes.
And can Kent inform us when and where we can see the video of this that you're going to be putting on the UNCA Spectrum site?
Oh, so he's saying it's going to be posted on the Ramsey Library YouTube page.
Yes. Ramsey Library, which is on the UNCA campus, and they have a YouTube channel. So if you go to the UNCA site and then find library, go to library, then there'd be, or just try YouTube with UNCA Ramsey Library.
All right. Well, thank you, everyone. Very enjoyable.